Hi everyone, welcome you all to the YouTube channel of DCC and NIT-A. Myself Mayur and today I'm going to discuss the problem C8kbf entry that came in CodeChef status 80. I hope you have already gone through the problem. The basic prerequisite is the pigeonhole principle, which is a pretty simple one. So the problem statement basically states that we'll be given a unrooted weighted tree with n nodes, where the vertices u and v are connected by an edge with weight w. Now the value of its simple path from x to y is defined as the bitwise XOR of the weights of the edges it consists of. Now our task is to find four vertices A, B, C, D such that A is less than B and C is less than D. Also the value of the simple path from A to B is equal to the path from C to D. So that is the basic requirement, and if there are no such vertices that satisfy the property, we will report that it doesn't exist. That is, we will just output -1. Else we will output ABCD. Now, if we take a look at the example, let's say if I just take this example, so this is the one. So you can see that if I just take this path, the actual value of this path means the value of this path is 3, and the value of this path is also 3. So what we can print is like we will print 1 3, then 1 3, then 2 and 4. So this will be our result, as you can see here. 1 4 2 and 3. So yeah, that is fine. So here they have made the path as like this one and this path, so that is also fine. The actual value will be 2, so like both are valid answers. Now what can we do about this? Like if we think like we'll go to all the possible path and check for all the values, that will be of course of a time complexity of n square, which will give clearly because the value of n is till 10 to the power 5. Now the next thing that may come to our mind is like if we can find any path whose actual value is 0. This is a preliminary thought, but still if you think more about this, you will see that like this doesn't lead to any satisfactory result, or like we don't get any proper output from this. Now the next thing that you need to note here is that like the what is the constraint, what are the constraints. That is a very important thing. So you will see that the value of w, that is the weight, it can go only up to 2 to the power 20, and 2 to the power 20 is like somewhere around 10 to the power 6, or in that range, like 1 is 6 range or something in that range. Yeah. So whatever the XOR value, like the maximum XOR value in the path, it will be at max 2 to the power 21 minus 1. So we only have 2 to the power 21 values from 0, starting from 0 to 2 to the power 21 minus 1. So we have 2 to the power 21 values, and that is around 2 into 10 to the power 6. So that is a feasible number, means that seems like a small number. Now what can we do about that? So now we'll see, like we'll apply here the pigeonhole principle. Let's say like if we just keep on finding the XOR value of various paths, we are just randomly selecting various paths and we are finding the XOR value, or like the value of that path, then in the worst case what will happen? First of all, we will find 2 into 10 to the power 6, or whatever be the value, like 2 to the power 21 values, 2 to the power 21 unique values of paths. Then whenever we will go to the next path, that 2 to the power 21 plus 1 path, then that value will be something from the previous ones only, as per the pigeonhole principle. I might sound somewhat confusing. Now I'll show it using an example. Here you can see let's say this is a tree. Now this is rooted at 1. So if I take the path from 1 to 2, the value will be 1. Then if I take the path from 1 to 4, the value will be 0. Now if I take the path from 1 to 3, the value will be 2. So these are the paths, like if I take, means if the paths originate from 1. Now what if the path originate from 2? So I have just drawn it here also, like for 2 to 1, this is I've already calculated this, so doesn't make much sense for calculating again. Now for the part 2 to 3, the actual value is 3, so I'll write 3 here. Now for 2 to 4, the exit value is 1. So here you can see that 1 has already come before, and again we are getting 1. So I know that this is a repeating value. So this is the pigeonhole principle. Like here I am assuming that the weight can be at max, means the weight range is between 0 and 2 to the power 1. So this is my range for weight. So you can see that, like, if we have only this much range, that is we have only three possible values: 0, 1 and 2. If the weight can be 0 to 2 to the power 1, so sorry, there are four possible values: 0, 1, 2, 3 of the there are four possible values of path: 0, 1, 2 and 3, if you consider the weight between 0 to 2 to the power 1. So we can have at most four distinct values of path. Now whenever we will go for the fifth path, like here we have already found four distinct paths, that is 1, 0, 2 and 3. Now whenever we went to the fifth path, we found that that value is something from the previous one, because that is the rule, we don't have any more distinct value, so it will repeat for sure and we'll get our result. So at max, how many checks we need to do? We will need to do 2 to the power 21 checks only, or 2 to the power 21 plus 1, like that is the rough estimate. So sometimes, like, you might get repeating edges, like here the edge between 2 to 1 or 1 to 2, that was repeating, so you might get some repeating edges, but that is fine. Still we'll have a have the range in the, means we have a feasible range. So now just let's take a look at the code. So here what I've taken is, like, initially I've taken n, and then I've created the adjacency matrix for this weight and edges. Now here I've taken just 0 based indexing. You can take 1 based indexing also. Now for just checking, like, whether, like, which values, means for just storing, like, which pair have what path value, what I did is, like, I have made a vector of 2 to the power 21 size. So whenever I get a path that has, let's say, the path value as x, then I'll store that path in that index, like vv of x will be that path, like the source and the destination. So that's why, yes, set of pair intended. And then what I've done is, like, I've just run a DFS from all the possible nodes. Like, I've started from 0, then 1, then 2 and so on. Here I've called the DFS, and then in the DFS, what I've done is, like, I've gone through all the adjacent nodes, like this is just the normal DFS, and now I'm finding the exit value also here. I'm finding the exit value. Now if that exit value doesn't exist, means if we don't have any previous path with that exit value, we'll just insert that in our set. We'll insert that pair in our set. Now if that exit value already exists and this is a different pair, like this is not the same pair, like this is not a repeating value, repeating path, so what we'll do, like, we'll make our answer equal to x. Here I have initialized answer to be -1, that means we have not found our answer yet. Now whenever we are assigning answer to x, that means we have found our answer, and so we are returning from here. We have also stored the pair here also in the vector. And lastly, like, here we are checking if our answer is not equal to -1, then we'll be printing it and then break, or else if at last the answer is still -1, then we'll be printing -1 because we did not find any result. So that was all for this code. This code might not be that much neat or clean, but I hope you got the logic. Now you can implement on your own. If you still have any kind of doubt, you can let me know in the comment section. I'll try to solve as soon as possible. Thank you.